So what happens when the magnitude of z is big? That is, very negative or very positive. And what constitutes big in the first place? You'll see that the z-table provided in the course material only goes up to 3.09. And that's associated with 0.4990 probability, or 0.001 in the tail. Okay, so if we have a standard normal random variable, mean 0 up to 3.09 is all that the z-table is going to give us. Okay, that is associated with 0.4990 probability between 0 and 3.09, or this tail area of 0.001. Similarly, down here, for negative 3.09, this tail area, of course, would be 0.001. Okay, that's a very small probability. Very few realizations lie down here in this tail below negative 3.09 or above 3.09, standard deviations away from the mean. Okay. Another way to think about that is 0.998 of possible values. 99.8% of values lie between this number and this number, between 3.09 and negative 3.09 standard deviations away from the mean. So the vast majority of realizations lie here. And that's why the table only goes up to those values. Okay, we're covering most of our bases with these two values. Okay. But what if we find a value that lies, let's say, 3.5 standard deviations away? For the purposes of this class, we can assume that the probability between 0 and 3.5 on the z-axis, here's 3.5 out here, okay? We can assume that this probability is 0.5 for the purposes of this class, okay? There's essentially no probability in this tail, okay? Here, at 3.09, there was only 0.001 probability up here. If we move this value of z a few more standard deviations away, or a few tenths of standard deviations away, we're essentially seeing no probability in this tail. And that's okay. Okay? So we could assume just 0.5 for this probability. Or we could use Excel to give us a little bit better estimate than 0.5. Okay? And that Excel function that we would use is the norm s dist function. Okay, the norm s dist function reads in a value of z and reports the cumulative probability from negative infinity up to that value. Okay, so if we have on the z-axis a value of z, the norm s dist function gives us this cumulative probability from negative infinity up to that value of z. Okay? So let's just say we plugged in 3.5. That is, we used the norm s dist function and plugged in 3.5 for z. It's probably not going to give us 1. Okay, that would be the cumulative area up to 3.5 that we would assume. But what does it return? It returns the value 0.999767. Okay, that's close to 1, but it's not quite. Okay, 0.5 is a pretty good guess for this area, but it's not exact. Okay, so this would be a better estimate of the area between negative infinity up to the value 3.5. That would suggest that this area right here, or let's just say this area right here, would be 0.499767. Again, pretty close to 0.5, but not quite. So of course you can use the norm s dist function for any of the problems that we've been talking about so far. Okay, if you don't want to use a z-table, you can always use the norm s dist function for any value of z, and you can interpret it as the area under the curve between negative infinity up to the value that you read in. Whether it's here, you can read in positive values and negative values, and you'll get a cumulative probability. But for pedagogical purposes, in any kind of stats class you'll ever take, we always start out using a z-table just so you get an idea of what this distribution looks like and how values under the curve change as the values of z change. But you can always implement a norm s dist function or any other kind of Excel function to describe many of the functions in this class.